Hello students, this lesson is on sequences. A sequence is an ordered list of infinitely many numbers. A sequence can be characterized as a function whose domain is the set of natural numbers, and whose outputs are the terms of the sequence. Predict the next few terms of each sequence below. Example 1, our list of numbers is 1, 2, 3, 4, 5, 6, etc. And we can predict the next one will be 7, and then 8, and then 9, and then 10, etc. The next sequence begins with a 1 and then a 2, and then a 1 and then a 2, and then a 1 and then a 2. Assuming this pattern continues, we would expect to see a 1 and then a 2, a 1 and then a 2, etc. This sequence is known as an oscillating sequence because the terms alternate between two different numbers. Now every sequence has a first term, and in the case of example 2, the first term is 1. A second term in this case was 2. A third term was 1 again. A fourth term was 2. This is what I mean when I said that a sequence can be characterized as a function whose domain is the set of natural numbers and whose outputs are the terms of the sequence. So in this case, the domain are these unseen orange numbers, which are simply the counting numbers, 1, 2, 3, 4, 5, 6, etc. And the sequence can be thought of as simply the list of all the outputs. Example 3, we have 1, then 1/2, then 1/3. So I predict the next term would be 1/7, and then 1/8, and then 1/9, etc. Example 4, we see that the signs are alternating between positive and negative, and furthermore, the magnitudes of the numbers are cutting in half. In other words, there appears to be a pattern. To go from one term to the next, we multiply by -1/2. -4 times -1/2 is +2. +2 times -1/2 is -1, etc. So continuing this pattern, if we multiply -4 by -1/2, we get +1/8. Multiply by -1/2 again, we get -1/16. So +1/32, and then -1/64, etc. This is known as a geometric sequence, which is a sequence that has a pattern of multiplication by the same number to go from term to term. Example 5, we have 1, 1, 2, 3, 5, 8, etc. This one can be challenging to determine the pattern. Notice the sum of the first two terms makes the third term. 1 plus 1 makes 2. Now add the second and third term, and we get the fourth term. 1 plus 2 is 3. Now add the third and fourth term to get the fifth term. Add the 3 and the 5, we get the 8. So I predict that adding the 5 and 8 will produce the next term, which is 13. And now we add 8 and 13 to get the next term, which will be 21. 13 plus 21 is 34. 34 plus 21 is 55, etc. This is known as the Fibonacci sequence, and was a sequence made popular in the movie The Da Vinci Code. Also has important connections to naturally occurring phenomena. Now the general form of a sequence. Every sequence has a first term, which we label as a sub 1. Second term we label as a sub 2. Third term a sub 3, etc. In general, we can say a sub n represents the nth term. So this 21 would be a sub 8, or in other words, the 8th term of the Fibonacci sequence. We can also write a of n to represent the nth term using classic function notation. For example, in the case of the Fibonacci sequence, I can keep track of the input variable n and then give the output variable. So when n is 1, a of 1, or a sub 1, was also 1, looking here on the Fibonacci sequence. When n is 2, the second term was also 1. When n is 3, this represents the third term, that became 2. The fourth term was 3, etc. So you can see that every sequence represents a function whose domain are the counting numbers and whose outputs are the terms of the sequence itself. Okay, next page. A sequence can be defined explicitly, meaning a rule is provided for directly calculating any term. Find the first 5 terms of the sequence defined by the following rule. Then graph those terms. Use technology to graph more terms. So here we have a sub n, standing for the nth term of a sequence, and it's given by this explicit formula. So if you want to calculate the first term, you simply change all the n's to 1 and calculate. We get 3 times 1, which is 3, minus 1 is 2, over 1, and we get 2. This can correspond to the point 1, 2, located here, where this 1 down here is a count, keeping track of what number term we're on, so the first term, and the output 2 is the actual first term. The second term of the sequence can be calculated from the explicit formula, change the n's to 2. So 2 times 3 is 6, minus 1 is 5, and then divide by 2, and we get 2.5. So the second term of the sequence has an output of 2.5. The third term will be 8/3, which is 2 2/3, which is 2.6 repeating, putting us roughly here. The fourth term will be 11/4, which is 2 3/4, or 2.75. And the fifth term will be 14/5, which is 2 4/5, which is exactly 2.8, roughly there. And we could calculate more terms by hand if necessary. However, let's next turn to technology to learn how to do this using Desmos in particular. We see our Desmos code. Now I'll go to the Desmos graphing calculator online. Begin by defining capital N equals any counting number, let's say 5. And then for the window of n, let's say 1 up to any whole number you want, let's just say 20. For the step size, say 1, and then hit enter. This creates a slider where we can drag n to any counting number beginning at 1 and ending at 20. The next line, say little n equals bracket, and 1, comma, dot, 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 comma, capital N. Now these commas aren't necessary, and this just created a list of numbers from 1 up to whatever capital N is. If you drag capital N back down to 5, you will see only 5 numbers in this list. In the third line, define the function, but use function notation, so a of, and then I'm going to use the input variable x instead of n, because Desmos is programmed to recognize x as an input variable. And then this equals, and then copy the explicit formula, except use x's, so 3x minus 1, all over x. Hide the image, I don't need to see it. And then in the fourth line, we create a set of points, where the first coordinate will be n, and the second coordinate will be a of n, using lowercase n's. You can click and hold here to bring up options for formatting. What this fourth line of code did was it took every single value of little n, of which there were 5 currently, plugged them into this function and got an output, and is now plotting these points over here in our graph. Let me change my settings here so the step size is 1 for both x and y. I will zoom out my vertical axis and compress my horizontal axis slightly. Now if you want to see more terms of the sequence, you simply have to drag capital N to higher numbers. Drag it to 6. Now we have 7 points, 8, 9, 10, etc., all the way up to 20. And here are the first 20 terms of the sequence graphed. Notice if I reveal the actual function, we get a continuous curve that passes through these points. Also notice that 3n minus 1 over n can be rewritten as 3n over n minus 1 over n, which is 3 minus 1 over n. And as n gets larger, this fraction will approach 0, meaning that this expression will approach 3 minus 0, which is 3, suggesting that we have a horizontal asymptote at y equals 3. Okay, let's go to the next page. Now, a sequence can also be defined recursively, meaning a rule is provided for calculating a term by using one or more previous terms. In such cases, at least one term should be known to establish the rest of the terms. Find the first 5 terms of the sequence defined by the following rule. Use 2 as the first term and then repeat the task using 4 as the first term. Okay, notice our subscript is n plus 1. And in our formula, we have a term that reads a sub n. If I let n equal 1, change all the n's in the statement to 1, we wind up getting a sub 2 is equal to 2 plus 1/2 a sub 1. If I change n to 2, change that n to a 2, add 1, so we get a sub 3 will be equal to 2 plus 1/2, and then change this n to 2 as well, times a sub 2. In other words, I can only calculate a sub 3 if I first know what a sub 2 is. If n is 3, we'll get the statement a sub 4 is equal to 2 plus 1/2 of a sub 3. So I can only calculate a sub 4 once I know what a sub 3 is. In general, wherever a sub n is, a sub n plus 1 will be the next term of the sequence. And this formula suggests I need to know this term before I can calculate this term. So in words, you can think of this as the next term, and a sub n relative to a sub n plus 1 would be the current term. Let's see what we get if we assume that the first term of the sequence was 2. Well, a sub 2 is equal to 2 plus 1/2 of a sub 1. And now we substitute this 2 into the a sub 1 position. So we get a sub 2 is going to be equal to 2 plus half of 2, or 2 plus 1, and we get 3. Now a sub 3 will be found by doing 2 plus 1/2 of a sub 2. Well, a sub 2 is this 3, and that'll be substituted right here. giving us 2 plus half of 3. That's 2 plus 3 halves, which is 4 halves plus 3 halves, or 7 halves. Now we are asked to find the first 5 terms. So a sub 4 will be found by doing 2 plus 1 half of a sub 3. 7 halves will be substituted in there. 1 half of 7 halves is 7 fourths, and add 8 fourths to that, and we get 15 fourths. And then finally, a sub 5 will be 2 plus 1 half of a sub 4. Substituted in for a sub 4. Half of that is 15 eighths, and 16 eighths and 15 eighths add to be 31 eighths. The sequence would be first term 2, next term 3, then 7 halves, then 15 fourths, then 31 eighths, etc. Notice that given a recursive definition, it would be difficult to jump ahead in the sequence, say to find the 100th term, because in order to know the 100th term, you need to know the 99th term, but then you need to know before that the 98th term, etc. Whereas for an explicit sequence, I can easily jump to the 100th term by simply changing the ends to 100 and calculating. Okay, let's repeat this task with 4 being the first term. Once again, according to our recursive definition, the second term will be equal to 2 plus 1 half of the first term. Substitute 4 in. Half of 4 is 2. Add to 2, we get 4 back. A sub 3 will be 2 plus 1 half of the second term. But once again, 4 gets plugged in for the second term, and that gives us a third term that's also 4. This will continue. The fourth term will still be 4. The fifth term will still be 4. And here we will have a sequence of all 4s forever. This is known as a constant sequence. So even though we had the same recursive definition that tells you how to go from term to term, the different choices in starting value made all the difference in determining what the sequence ultimately would be. Okay, moving on to the next page. A sequence is convergent if its terms approach a single finite number as n approaches infinity. Otherwise, it is divergent. Sequences that are convergent basically have a horizontal asymptote. So this sequence was a sequence that approached 3, so we would say this is a convergent sequence, where the terms converge to 3. A sequence is monotonic if it eventually becomes an increasing, decreasing, non-decreasing, or constant sequence. This word eventually is important because a sequence can maybe initially be erratic, but as long as it eventually settles into some sort of monotonic pattern, such as a sequence that's increasing, from this point on, we will still say that this entire sequence is monotonic. Now, a sequence is bounded if all of its terms lie within some window of finite width. Otherwise, the sequence is unbounded. So imagine 2 horizontal lines when you're graphing the sequence. If all of the terms stay within these horizontal lines, it may be one of the lines gets approached, but we would call this a bounded sequence. Now graph each sequence and comment on its convergence, monotonicity, and boundedness. I will take the approach of doing this by hand. So in the first case, when n is 1, we get 2 minus 1 over 1, or 2 minus 1, we get 1 back. When n is 2, we get 2 minus a half, which is 1.5. When n is 3, we get 2 minus a third. So start at 2 and come down a third. When n is 4, we get 2 minus a quarter. And then we get 2 minus a fifth, and then 2 minus a sixth, and 2 minus a seventh, 2 minus an eighth. We get a sequence that's getting closer and closer to 2. Well, this sequence is convergent, and it's convergent to the value of 2, which is easy to spot because 1 over n, as n approaches infinity, shrinks to 0. So the overall sequence terms will approach 2. This sequence is also monotone because it is from the very start an increasing and forever increasing sequence. And this sequence is bounded because here is a window of finite width that contains all the terms. Okay, the next sequence, when n is 1, we get 2 minus a half, which is 1.5. When n is 2, 2 times 0.5 is 1, and 2 minus 1 is 1. When n is 3, we get 2 minus 3 times 0.5 is 1.5, and 2 minus that is 0.5. In fact, this is just a linear sequence. We lose 1 half as we go from term to term. This expression as n approaches infinity, half of infinity is infinite in size, and 2 minus that is negative infinity. So we say this sequence is divergent because it does not have a finite limit. It is monotone, decreasing sequence in this case, and there is no window of finite width that can contain the entire sequence. There is a upper bar that the sequence will never go higher than, but no matter what lower bar, the sequence will eventually go lower than it. So we say that this sequence is bounded above but not bounded below, but we'll just say unbounded. Okay, next page. Graph each sequence and comment on its convergence, monotonicity, and boundedness. So the same instructions. Here we have radical n. When n is 1, the first term is radical 1, which is 1. When n is 2, we get radical 2, which is about 1.4. When n is 3, we get radical 3, which is about 1.7. When n is 4, we get radical 4, which is 2. Radical 5 is a little more than 2. Radical 6 is even higher than that. Radical 7 is higher than that. Radical 8 is even higher than that. Radical 9 finally gets us to a height of 3. This is a sequence, as n approaches infinity, that the terms of the sequence will also approach infinity. And so we say the sequence is divergent. The sequence is monotone, increasing, and because the terms go up forever to infinity, they increase without bound. This sequence is unbounded. And now the next case, n is now a power, 1 plus negative 1 to the n. When n is 1, negative 1 to the 1 is negative 1. Add to 1 is 0. When n is 2, negative 1 squared is positive 1. Add to 1 is 2. When n is 3, negative 1 cubed is negative 1 again. Add to 1 goes back to 0. When n is 4, we'll get 2 again. And this will become an oscillating sequence where the terms bounce back between 2 and 0 forever. So this sequence does not approach a single output. So we say divergent. Nor is the sequence monotone, because terms increased, then decreased, and then increased, and then decreased. So it is not monotone to start, nor does it eventually become monotone. So we'll simply say not monotone. However, the sequence is bounded. Here's a pair of horizontal lines between which all the terms of the sequence will lie. All right, the next sequence. When n is 1, we have sine of 1. And I will reach for a calculator for this. The sine of 1, and make sure that you are in radian mode, is about 0.84. The sine of 2 is about 0.9. Sine of 3, about 0.14. Sine of 4 is about negative 0.75. Sine of 5 is close to negative 1. Sine of 6 is about negative 0.3. Sine 7 about 0.65. Now what's happening here is we are getting a sequence whose outputs correspond to points that are along the curve sine of x, which crosses the x-axis at pi, which is just past 3, and again at 2 pi, which is just past 6. As n approaches infinity, this sequence does not approach a single output, so we say it is divergent. The sequence also is not monotone. It never settles into increasing or decreasing only. It forever toggles back and forth between increasing and decreasing, so not monotone. But the sequence is bounded. All the terms of the sequence lie between negative 1 and 1. The next sequence just has a 2 in its definition, so this is a constant sequence where the first term is 2, so is the second term, so is the third term, etc. This is trivially convergent. It does approach 2. In fact, it's always 2. It is also monotone, and a sequence is monotone if it eventually becomes increasing, decreasing, non-increasing, non-decreasing, or constant. This is a case of being monotone because the sequence is constant. And the sequence is clearly bounded. Here are a pair of horizontal lines that contain all the terms of the sequence. All right, the next example. When n is 1, this will be a 2, and negative 1 squared is positive 1. Add to 1 is 2, and then over a 1. So we get 2 over 1, which is just 2. When n is 2, this power is a 3, and negative 1 cubed is negative 1, and add to 1 is 0, and 0 will be over a 2, which is just 0. Now when n is 3, this exponent will be 4, and negative 1 to the 4th is positive 1, so we get a 2 in the numerator again, but will be over a 3, so we get 2/3. When n is 4, the numerator will be 0 again, and 0 over 4 is just 0. In fact, anytime n is even, the numerator will be 0, giving us a result of 0. When n is 5, we get 2 over 5, so 2/5. In fact, all these non-zero terms, this one was 2 over 1, this was 2 over 3, 2 over 5, 2 over 7, 2 over 9, etc. So you can clearly see that the denominator is growing while the numerator stays 2, so the non-zero terms are shrinking. This is an interesting sequence because half of the terms are already at 0 and the other half of the terms are decreasing to 0. So this is a sequence that does approach 0 as n approaches infinity. So we have a convergent and convergent to 0 sequence. However, the sequence is not monotone because we had a decrease followed by an increase and then a decrease and then an increase, and this will forever switch from decrease to increase. So not monotone, but the sequence is bounded. Here's a lower bound, here would be an upper bound. Okay, and the last example on this page, when n is 1, we get negative 1 over 1, which is negative 1. When n is 2, we get positive 1 over 2, so 1/2. When n is 3, we get negative a third, then positive a fourth, then negative a fifth, then positive a sixth. Here are our terms. We can see them alternating in sign, but the terms are shrinking to 0. The positive terms and the negative terms both are getting closer to 0, so we say convergent to 0. Not monotone because we had an increase in terms, then a decrease, then increase, etc. But the sequence is bounded. Here's an upper and lower bound containing all the terms of the sequence. All right, next page. Here are some sequence theorems. Indicate whether each statement is true or false. If you claim false, provide a counterexample. First of all, this symbol right here is an implication arrow. It means that if this is true about a sequence, then this must be true about that sequence. And we want to determine if this is a true implication or a false implication. So are all convergent sequences bounded? Looking at some of these examples, every single convergent example was also bounded, but would that be true in general? And the answer is yes. So looking at this case, for example, eventually all the terms get really, really close to 0, and there's only a finite number of terms that proceed, so it must be true that we can contain all the terms within a horizontal window. So this is a true statement. How about the reverse implication? Does a bounded sequence imply a convergent sequence? Well, we can see a counterexample to this right here. Here's a bounded sequence that is not convergent. Here's another bounded sequence that is not convergent. So we get to say false, and here's our counterexample, because this produced an oscillating sequence, which is bounded but not convergent. Now the third statement, does monotone imply convergent? Well, looking at these 6 examples, I see an example of a monotone sequence that's divergent. This is a false statement, and a good example is the square root of n. It is monotone increasing, but it is not convergent because the sequence approaches infinity. Does convergent imply monotone? The fourth statement. Looking at our examples, we have an example of convergent but not monotone. Another example of convergent but not monotone. So using that last example as a counterexample, we say this is a false statement. Negative 1 to the n over n is a good example of a convergent sequence that's not monotone. And then finally, does bounded and monotone imply convergent? So looking at these examples, the only one that was both monotone and bounded was this example here, and it was convergent, but it was also a constant sequence. So is it generally true that bounded and monotone imply convergent? Looking back at the previous page, here's another example of being both bounded and monotone, this time monotone increasing, so non-constant, and this one was also convergent. It turns out, and we won't take time to prove this, but this is a true statement that if a sequence is both bounded and monotone, that sequence must have a limit and must be convergent. For the sake of our class, we will move on. This page is a refresher of a principle known as L'Hopital's rule that was learned in a Calculus 1 course. It says that if the limit, as n approaches infinity, of a fraction of sequences has the form infinity over infinity or 0 over 0, and these are called quotient indeterminate forms, then this limit that we're after can be found by doing the same limit as n goes to infinity of a fraction of sequences which are found by differentiating the sequences a and b, provided this new limit exists or is plus or minus infinity. For example, find the limit below. If you break this down, 4n as n approaches infinity. Natural log of n also approaches infinity. Recall that the graph of natural log of x is as shown here. Even though the graph of natural log of x flattens out, it does not have a horizontal asymptote. Any horizontal line you could possibly draw, this graph will eventually go higher than it. So the natural log of n will approach infinity as n approaches infinity, although very slowly. In the denominator, this radical n and this 3n both will approach infinity as n approaches infinity. So overall, this fraction will approach infinity plus infinity, which is still infinite, over infinity plus infinity, which is still infinite. This is a trigger for the use of L'Hopital's rule. So we get to instead consider the limit as n goes to infinity, and we differentiate as if n is a continuous variable, both the numerator function and the denominator function. So the derivative of 4n is just 4, and the derivative of natural log of n is 1 over n. The derivative of radical n is 1 over 2 radical n. and the derivative of 3n is 3. And then we reassess. As n goes to infinity, notice where the n's are now, they're only in denominators. So this will approach 1 over infinity, which is 0, and this will approach 1 over infinity, which is also 0. So overall, this fraction will approach 4 plus 0, which is 4, over 0 plus 3, which is 3. So we get 4/3. Thus, we get to conclude that the original limit, as n approaches infinity, of 4n plus natural log of n over radical n plus 3n will be equal to 4/3. Let's confirm this with technology. I'll graph the function but using x's. Then I'll graph the asymptote we just found, y equals 4/3. And you can see the asymptotic behavior occurring. All right, let's go to the next page. Find the following limits. We use L'Hopital's rule 3 times. As n approaches infinity, we get infinity plus infinity, which is an infinite numerator, and we get infinity minus 1, which is an infinite denominator. So this triggers L'Hopital's rule. So differentiate the numerator, we get 2n plus 1. Divide by differentiate the denominator, we get 6n squared. And then reassess. This will still approach infinity over infinity. So that means we got to use L'Hopital's rule on this sequence. And we can continue this until we no longer have an indeterminate form. So differentiate the numerator, we get 2. Differentiate the denominator, we get 12n. And this time, we get a fraction that approaches 2 over infinity, which is effectively approaching 0. Which means that the limit prior is also 0, which means the original limit is 0. Now you may recall another way to do this problem is by recognizing that this is a rational function because it's a second-degree polynomial divided by a third-degree polynomial. And we can algebraically manipulate this by taking the highest power from the denominator, which is 3, and multiplying this fraction by 1 over n to that power, so 1 over n cubed, over itself. Because this fraction here is equal to 1, now we distribute the 1 over n cubes and simplify. We get n squared over n cubed, that's 1 over n, plus n over n cubed, that's 1 over n squared, all over 2n cubed over n cubed is 2, and minus 1 over n cubed. And now we have 3 fractions with n's in the denominator that will all approach 0 as n goes to infinity, suggesting that the value of this limit will be 0 plus 0 over 2 minus 0, 0 over 2, which is just 0, confirming what we got with L'Hopital's rule. Now the middle example, this approaches infinity over infinity again, so we can use L'Hopital's rule and do a limit as n goes to infinity of instead the derivative of the numerator is 2n plus 1 over, and the derivative of the denominator is 4n. This still approaches infinity over infinity, so apply L'Hopital's rule one more time. The derivative of the numerator and denominator are 2 and 4, and this is now a constant sequence that has a limit of 2/4 or 1/2, which means that this limit was 1/2, which means that the original limit was 1/2. Or I can go back to the original setup, identify the highest power from the denominator, which is 2, multiply this by 1 over n to that power, so 1 over n squared, over itself, distribute and simplify, and we get 1 plus 1 over n all over 2 minus 1 over n squared. Well, these two fractions here, as n approaches infinity, will approach 0, so this limit will be 1/2, confirming what L'Hopital's rule gave us. And now the third case. As n approaches infinity, we get infinity over infinity. So apply L'Hopital's rule. The derivative of the numerator is 2n plus 1. The derivative of the denominator is just 2. And this time, as n goes to infinity, we approach infinity divided by 2, which is still infinity in size, which means that the original limit was also infinity, so this was a divergent sequence. In the algebraic approach, the highest power in the denominator is an implied 1 on that n, so multiply this by 1 over n to the 1 over itself. Distribute, we get n plus 1 over 2 minus 1 over n. And as n goes to infinity, that numerator approaches infinity, while this fraction here shrinks to 0, meaning that this approaches infinity over 2, which is still infinity, confirming L'Hopital's rule. Now all three of these were rational functions, and you may recall that if you compare the degrees, degree 2 over degree 3, I call this a bottom-heavy rational function, and all bottom-heavy rational functions will approach 0 as n goes to infinity. This middle case, we had square over square, so this I refer to as balanced. It will always be the case that if you have a balanced rational function, that the limit will be the ratio of the leading coefficients. So there's an implied 1 in front of this n squared, and there's this 2 in front of the n squared. So our limit will be that 1 over that 2. And in the last case, we had a degree 2 over an implied degree 1. This I refer to as top-heavy because it's a higher degree in the numerator than it is in the denominator, and all top-heavy rational functions will have an infinite limit, either plus or minus infinity, as n approaches infinity. So they will be divergent sequences. All right, the next page. Here we explore other indeterminate forms. We've already explored the two kinds of quotient indeterminates, infinity over infinity and 0 over 0. There's also a scenario known as a product indeterminate, which is infinity times 0. If you have a sequence that's one factor approaching 0 and the other factor approaching infinity, you sort of have a tug of war. It's tempting to say that 0 times anything is 0. It's also tempting to say that infinity times anything is infinity. So what happens when you have 0 times infinity? Which one wins out, or is there some balance that they strike? A difference indeterminate has the structure infinity minus infinity. Will the infinities cancel each other perfectly and get 0, or will one infinity sort of outweigh the other infinity? Or will there be some sort of compromise or balance that they strike? Then you have what are known as exponential indeterminates. If you have a sequence approaching 1 being raised to a sequence that's approaching infinity, this is an indeterminate scenario. Infinity to the 0 is indeterminate, and 0 to the 0 is indeterminate. In this slide, we will address these three. Let's look first at a product indeterminate. This will be a limit as n goes to infinity of 3n times sine 2 over n. Now this 3n will approach infinity, but this 2 over n will approach 0, so this sine 2 over n will approach sine of 0, which is 0. So overall, we have the limit of a sequence that's infinity times 0. This is a product indeterminate. So what we need to do is find some way to express this as a quotient indeterminate and then use L'Hopital's rule. L'Hopital's rule should only be applied when you're looking at an infinity over infinity or a 0 over 0. It must be a quotient indeterminate before you apply it. Now in this case, the easy way to accomplish turning this product indeterminate into a quotient indeterminate is to just do some algebraic manipulation. We'll keep the 3 next to the sign of 2 over n, but instead of multiplying this by an n, I'm going to divide by its reciprocal, so divide by 1 over n. And now we have a situation where the numerator approaches 3 sine 0, which is 0, and the denominator approaches 1 over infinity, which is also 0. So this is a trigger for L'Hopital's rule. It is one of our indeterminate forms. So we get to differentiate the numerator. The 3 stays, derivative of sine is cosine, the argument stays the same. But don't forget the chain rule. Now we multiply by the derivative of the argument. And that's a 2 times n to the minus 1 would give us negative 2 n to the minus 2, which is negative 2 over n squared. And then all over, and then differentiate the denominator. A 1 over n is n to the minus 1, and its derivative is negative n to the minus 2. In other words, negative 1 over n squared. Now we get some cancellation. The n squares cancel, and the negative and the negative become positive. So this winds up just becoming the limit as n goes to infinity of 2 times 3, which is 6, cosine of 2 over n. And this sequence will get closer and closer to 6 cosine of 0. Cosine of 0 is 1, so this will just be 6, which means that the original limit is 6. Okay, now let's explore a difference indeterminate. As n approaches infinity, this exponent 2 over n approaches 0, but this n and this n both approach infinities. This approaches e to the 0, which is 1. 1 times infinity is infinity. So the end structure here is that this is approaching infinity minus infinity. In this case, let's do some factoring. Factor an n out, leaving e to the 2 over n minus 1, and reassess. The n in front approaches infinity, but the inside here approaches e to the 0 minus 1, which is 1 minus 1, which is 0. So we've converted this difference indeterminate into a product indeterminate of the form 0 times infinity. So we still want to turn this into a quotient indeterminate. And again, I'm going to take that coefficient n and put that into a denominator. So our numerator is e to the 2 over n minus 1 over a 1 over n. And now we finally have approaching a 0 over 0 as n goes to infinity. This is a trigger for L'Hopital's rule. So differentiate the numerator. The derivative of e to the 2 over n is itself, and then times the derivative of the exponent, which we saw was negative 2 over n squared, over the derivative of the denominator, which is negative 1 over n squared. This simplifies to simply 2 times e to the 2 over n. This will approach 2e to the 0, which is just 2. This means that our original limit was just 2. And now we have an exponential indeterminate. As n approaches infinity, this fraction approaches 0, so the inside approaches 1, but the exponent is approaching infinity. So this approaches a 1 to the infinity, which is one of our 3 exponential indeterminate forms. Well, to simplify this, we're going to use a property of logarithms. The e to the natural log of something is equal to that something. And you might also recall the natural log of a to a power is equal to that power times the natural log of a. So I'm going to begin by manipulating this expression. And for convenience sake, I'll stop writing the limit. But we can begin by writing that 1 plus 1 over n raised to the n is the same thing as e raised to the natural log of this same expression. Now we're going to use this second log property, this exponent, n, and moving it down as a coefficient on this natural log. So we get e raised to the n times natural log of 1 plus 1 over n. If I pause right here and consider the limit of the exponent, as n goes to infinity, this exponent approaches infinity times natural log of 1, but natural log of 1 is 0. This is a product indeterminate. So I'm going to rewrite that exponent as natural log of 1 plus 1 over n over a 1 over n. And our exponent is starting to get a little unwieldy, and so it can be helpful to do something like this and say e raised to the, and then just put all this in parentheses. As a function, this exponent now approaches a natural log of 1, which is 0, over a 1 over infinity, which is also 0. So we can use L'Hopital's rule, and we can use L'Hopital's rule only on the exponent. So we have e raised to the, differentiate the numerator with natural log of a function, so we do 1 over that function, and then times the derivative of that function, which is negative 1 over n squared. And then differentiate the denominator, we get negative 1 over n squared. Here we get perfect cancellation of this term and that term, giving us e raised to the 1 over 1 plus 1 over n, and this whole expression will approach e raised to the 1 over 1 plus 0, so 1 over 1, or just e to the 1. In other words, just e. Let me move this out of the way. So our original limit is going to just be e. Now take note that the following are not indeterminate forms. If ever you have a sequence that's approaching infinity over a 0, this will just be infinite in size, conclusively. Whereas a 0 over infinity will be 0 in size. A 1 times infinity will be infinite in size, and an infinity plus infinity will be infinite in size. And 0 to the infinity will be 0 in size, and infinity to the 1 will be infinity in size. It's these forms that trigger additional analysis. If you get one of these forms, you must find some algebraic way to put that form into one of these two forms so that you can then use L'Hopital's rule. Okay, last page. I'm introducing what I call the domination chain of non-decreasing sequences. So we have different categories of non-decreasing sequences, and I'm sorting them by their growth potential. Now think of n as the variable that's approaching infinity, and all the other letters you see here as constants. At the bottom of our domination chain is a simple constant. Something that grows faster than constants are logarithms, as long as this base right here is more than 1. If the base is more than 1, this sequence will eventually approach infinity, which will overtake eventually any constant. To illustrate this, let's graph a constant y equals 5 and graph a function that's a logarithm. Let's just do log base 10 of x. Remember, if the base is 10, I don't need to put a base here. But if you want to do a log base 3 of x, you can pick any log base you want as long as the base you pick is more than 1. You can even do a natural log of x, which is a log base e. But it doesn't matter which log you pick as long as the base is more than 1. And on this current window, it looks like that the constant is higher than the logarithm. But if I hold shift and shrink and condense only the x-axis and do this enough times, you will see that eventually the logarithm will overtake the 5. Now this is true even if I put a larger number here, like 10. Continue to contract the x-axis, and you can see that eventually when x is large enough that the logarithm will overpass the constant. So in our notes, we introduce a symbol. It's a double alligator mouth, if you will. And we use this notation to mean that the greater or the dominating sequence, which is logarithms in this case, will eventually overtake the lesser or dominated sequence, which is constants. And the key word here is the word eventually. In our imagery, if these were sequences, we would have had to go out to more than 22,000 terms before we finally saw the green sequence overtake and forever overtake the purple sequence. Now next, powers of n will eventually dominate logarithms as long as this power is more than 0. Now exponentials, as long as the base is more than 1, will eventually overpower powers of n. N factorial. Recall what a factorial means. Like a 3 factorial, for example, is 3 times 2 times 1, giving you 6. And a 4 factorial is 4 times 3 times 2 times 1, giving 24. But factorials will ultimately grow faster than any exponential once you go far enough out in the terms of the sequence. And at the top of the domination chain are n raised to the n. This will eventually overtake factorials. Now sort the sequences by domination. There are 7 sequences here. Constants will be on the low end of the domination chain. So here's a constant 1000, and I'll leave off the curly brackets. So 1000 will be at the bottom of our domination chain. Next will become logarithms. So that will come next in our list, natural log of n. Next are powers of n. So we're looking for n raised to a power. Well, I see an n raised to the 4, and I see a cube root of n. Keep in mind that that's equal to n raised to the 1/3. Here we have 2 sequences from the same class. They're both powers of n. Now the greater the power, the greater the growth potential. So to sort these, the dominated sequence would be n to the 1/3, and what dominates that sequence will be n to the 4th. All right, next we're looking for exponentials. I see 2 exponentials, and these can be sorted by the greater the base, the greater the growth potential. Now both bases have to be more than 1 for these to be growing exponentials. But the smaller base, the 1.1, won't grow as quickly as the larger base, 10 to the n. And then finally, any factorials, well, here's an n factorial. This will be at the top of our domination chain, because I don't see any n to the n's here. I'll leave it to you to graph all of these sequences and see that, compare any 2 sequences, and eventually the one on the right will overtake and forever take the one on the left. And finally, determine the limit of each sequence below as n goes to infinity. Natural log of infinity is infinity. Infinity to the 4th is also infinity. So this triggers L'Hopital's rule, derivative of the numerator, derivative of the denominator. You could simplify this, or you can assess right now, because the numerator now approaches 0 and the denominator approaches infinity. This is not an indeterminate form. This is equal to 0. So the original limit is 0. Now what we should learn here, the numerator and denominator are coming from 2 different classes of functions in our domination chain. We have a log divided by a power of n. And powers of n dominate logarithms. And because the power of n is in the denominator will overpower the numerator, which is why we're getting 0 as a limit here. So this middle case, as n goes to infinity, this does approach infinity over infinity, but L'Hopital's rule doesn't really work here because we don't know how to differentiate n factorial. We will trust on the domination chain that because n factorial dominates 10 to the n, that the numerator infinity will overpower the denominator infinity, and this will be infinite in size. Now this third case, we have 2 kinds of functions from the same class. The numerator will approach infinity as n does, and so will the denominator. So let's use L'Hopital's rule on this one again. The derivative of the numerator is 1 over the argument, and then times the derivative of the argument. And the derivative of the denominator is just 1 over n. And then we can simplify this. It'll be 2 over 2n plus 1 times n over 1, which will be 2n over 2n plus 1. And this is a balanced rational function. We could use L'Hopital's rule on it, but we also know, because this is balanced, that the limit will be the leading coefficient 2 divided by the leading coefficient 2, which is just a limit of 1. So this limit up here is equal to 1. Okay, and this concludes our lesson on sequences.